Hello, and welcome to APICS Extra Live, Streamline Your Operations, a Lean Primer with Peter J. Sherman and Michael A.M. Bork. My name is Kia Wood, editor at APICS. Before we begin, I'd like to run through a few details. At the end of the presentation, we will save time for a question and answer session. If you look at the right toolbar on your screen, you will see a questions box. To ask your question at any time during the presentation, simply type it in the box and click Send. If you experience any technical difficulties during today's broadcast, please call GoToWebinar Tech Support at 1-805-617-7000. Again, that's 1-805-617-7000. This presentation is being recorded and will be available on the APICS YouTube channel early next week. All registrants will receive an email with a link to the recording once it is available. And now it is my pleasure to introduce our speakers for today. Peter J. Sherman is Managing Partner at Riverwood Associates, a Lean Six Sigma certification training and consulting firm based in Atlanta. He holds a master's degree in civil engineering from the Massachusetts Institute of Technology and an MBA from Georgia State University. From 2008 to 2011, Peter served as lead instructor for Emory University's Six Sigma certification program. Peter has authored more than 60 articles on process improvement and quality. Peter is an APICS certified supply chain professional, a certified Lean Six Sigma black belt, and ASQ certified quality engineer. Michael A.M. Bork is senior engineer at Proterra Inc., a world leader in electric vehicle technology. He holds a bachelor's degree in mechanical engineering with a minor in manufacturing development from Michigan Technological University. Michael is a certified Lean Six Sigma Green Belt, a certification he received through Riverwood Associates, and has been a strong proponent in Proterra's development towards lean manufacturing. Both Peter and Michael co-wrote the APICS magazine January-March 2018 feature article, A Primer on Attaining High Impact Flow, which is available online at apics.org/magazine. Everyone, please give a warm welcome to Peter Sherman and Michael Bork. Peter and Michael, you may begin.
Thank you, Kia, for that introduction, and good afternoon, everyone on the webinar. Michael and I are going to be walking you through a primer on this topic called Lean to streamline your operations. And I'm going to be covering part of the material. Michael will be sharing some experience with his company at Proterra applying these principles. So I think you're going to enjoy this. Our agenda is as follows. We're going to set the stage with the challenge that companies face today. And then I'm going to define this concept of lean, and we're going to get to understand this very, very important concept of flow. Then we're going to segue into this three-step approach to streamlining your operations, which comprises determining your demand, assessing your capacity, and then balancing the line. And we're going to wrap up with some Q&A and any next topics. So with that, let's get into our challenge. There's a lot of explosive growth in e-commerce and green technologies these days. Our customers are expecting faster turnarounds than ever. Companies like Amazon have redefined the concept of what lead time used to be. Now it is from what was a few days to get a book to now instant within 2 hours, say, if you're a Prime customer in Atlanta, Georgia. Doing more with less. This is becoming more and more prevalent throughout industry. So the central question is, how do I streamline my operations to meet these demands? Before we get into the details, I'd like to just present a lean overview. Now, these two gentlemen here on the left, Henry Ford of the Ford Motor Company and Taiichi Ono, production manager for the Toyota Motor Works, were the originators of the concept of lean. And we say that lean focuses on the value by eliminating waste and accelerating the velocity of processes. Now, that's quite a rich statement. The value that lean focuses on is what my customer would pay for. And that central question is, if they're willing to pay for something you do, that's considered value. If what you do in the operation is something they wouldn't pay, that's non-value. The waste is generally swirling around us. Everything from overproduction to excess inventory, idle time, etc. And finally, this concept of accelerating the velocity of processes. We're not talking about trying to work faster, but what we're looking at is, from an end-to-end perspective, how can we reduce that lead time from order to ship, or from invoice to collect, or if you're in the R&D world, from ideation to prototype, and maybe prototype to commercialization. The faster you can accelerate those lead times, those processes, the reality is you're less susceptible to making mistakes. And it, of course, creates a much better experience for your customer. Now, the two key concepts of lean involve eliminating the waste and shortening those cycle times. Typically, we know those cycle times of order to ship, or it could mean requisition to receipt, invoice to collect. Now, take a look at some of these attributes of lean organizations, because they are truly unique. Half the human effort involved, half of the defects. Lean organizations essentially can double their capacity because they have those inherent traits. A third of the traditional engineering design efforts, using half of the floor space. And can you ever imagine carrying 90% less inventory in your business? No room for error, razor thin. But lean organizations have demonstrated that ability to do these things. Now that we understand the principles of lean, let's tackle this concept of flow. Literally, flow refers to the smoothness of how work is performed. And it's a core principle of our lean philosophy. Now, flow has some incredible benefits. It enables organizations to do a very much benefits. Ability to deliver products and services in a shorter period of time, known as lead time. Good flow results in less work in process, or commonly known as WIP, which in turn means there's less space. And when there's less WIP, there's also less chance to damage that WIP. Fewer mistakes. No more lost inventory, no more obsolescence, less damaged product. Flow gives you an incredible level of flexibility and responsiveness to your customer changes. So these are some very, very key attributes of why flow is so important. Well, now that we've understood what it is, let's get into the two types of flow. There is a push type of flow. And when you think of that, it's replenishing those goods or services based on a demand forecast or what we think the customer wants. And in supply chain, we know this term as build to stock. The other type of flow is more of a pull, replenishing those goods or services based on actual customer demand. And in our supply chain vernacular, we know this as build to order. So the question on the table is, which is better and why? Well, it depends. It depends on the nature of your business. Here is a table that captures these two flows, and I'm going to address the push first. Push is generally appropriate for businesses with long lead times. So for example, in the automobile industry and heavy equipment industries, or industries that are cyclical in nature, where they're needing to build up inventory for holidays. Push is the approach that those types of organizations take. Pull, on the other hand, is very, very effective in businesses that generally have short lead times. So for example, fulfilling an online book order. Amazon is a classic example. Or businesses that have very short shelf lives. For example, perishables such as food or even medicine. They have got to be produced based on what we call pull. Pull also applies to very customized and complex products, because it doesn't make sense to build an airplane, for example, at Boeing based on what we think the customer is going to need. And Michael, I'd like you to weigh in at Proterra. What type of flow do you guys utilize?
Yeah, absolutely. Thank you, Peter. So kind of as you were just indicating with industries that you see a lot more high variance, such as the aerospace industry, we at Proterra share a very similar system. We're a pull system due to the fact that our customers enjoy a wide variety of aspects to go into their vehicle.
Thank you. All right, so now that we've defined lean and the different types of flow, let's jump into this three-step approach to streamlining your operations. And here are those 3 steps. First, we need to determine our demand. Second, assess the capacity of our operation. And with those 2 items, we're in a position to balance the line. So with that, Michael, I'd like you to address this first step, if you could.
Absolutely. So as Peter had indicated in the previous slide, the first step in our 3-step process is to determine customer demand. Now, there are a number of different ways to acquire this information. First of which, you could look at historical orders, use those to project future numbers. Additionally, you could track sales and forecasting numbers as well in a similar fashion. Product development also can play a big part in shaping and determining customer demand, along with marketing programs as well as operations. And finally, you can ask the customer themselves. I mean, there's no better person to ask than the person you're selling to what they want and when they want it. So knowing the rate of customer demand allows you to synchronize production, which additionally allows you to optimize labor and equipment, which simultaneously reduces inventories to a minimum. So now that once we have determined customer demand, we can move on to the next step in our process, which is determining takt time. Takt time comes from the German word Taktzeit, which means beat time or heartbeat. Takt time sets the pace for production to match the rate of customer demand. The time to produce 1 unit of product to meet customer demand, that's takt time in essence. And there's a very simple formula that can be used to determine the takt time of a process. It is the available operating time divided by customer demand. So knowing this formula, we're going to go ahead and we're going to jump right into an example. In our example, we have a fulfillment center. And at this fulfillment center, the demand is 10,000 orders per month or 500 orders per day. The hours of operation are 8 a.m. to 5 p.m. with a half-hour lunch and 2 15-minute breaks. Now, the objective of this scenario is to find out what is the daily takt time at this fulfillment center and how does takt time differ from process time. So, remembering the formula from the previous slide where available operating time divided by customer demand will yield us the takt time, we're going to take a look at our available operating time, which 8 hours translates into 480 minutes. And we're going to break it down into minutes, so that way it's a more finite and easily digestible number. It'll also help us to determine further calculations later in this presentation. So 8 hours or 480 minutes divided by 500 orders per day yields a takt time of 0.96 minutes per order. So this takt time in essence means that one order should be completed in approximately 1 minute in order to meet our customer demand. Notice how takt time ignores the amount of labor or machines involved with our process. So now that we have takt time and understand customer demand, we're going to go ahead and move on to the next step. And Peter, would you be so kind to explain step 2 in our process?
Yes, thanks, Michael. Okay, so step 2 involves calculating capacity. And when we talk about capacity, in essence, we ask this question: what's the capacity of my fulfillment center or the capacity of my manufacturing operation? In other words, how many units can be filled or produced each day in my current operation? And the way to calculate capacity is the available production time. And when we say available, we strip out the lunch breaks, the morning, afternoon breaks, any uninterrupted or any unexpected downtime due to equipment failure and so forth. What's available divided by the process time per unit. Now, to answer this question, we have to determine the process time at each step. And when we talk about process time, think of that as the amount of time actually spent working on a step. So here's an example in a fulfillment center. There's a picking stage, and that takes 30 seconds to pick those items. Next, those items are inspected to match the manifest or the pick sheet, rather, and that takes 10 seconds. And then the items are packed, filled up, maybe a minute. They're labeled, they take 10 seconds, and then finally they're sealed up, 5 seconds, ready to go to the loading dock. So back to our example, that same fulfillment center is 10,000 orders per month or 500 orders per day. Hours of operation are 8 a.m. to 5 p.m. with a half-hour lunch and 2 15-minute breaks. What is the capacity at each step? So remember, capacity, taking my available operating time divided by the process time at each particular step. So here's the value stream we see up here. And the capacity, for example, at step 1 is the 480 minutes. We have to strip out the half hour for lunch and the 2 15-minute breaks, divided by 30 seconds, or we can call it a half a minute per item. And we get 960 items that could be picked during the day. That's the capacity. The table here at the right shows the capacity for all 5 steps. And this is in a day, and you could see step 5, the seal operation, which only takes 5 seconds, literally has a capacity of 5,760 items that could be sealed. So this is what we call capacity of the operation. Step 3 is that limiting operation because it's the longest step, which leads us to this concept called the bottleneck. The bottleneck, we've heard it a million times. Think of it as the limiting resource, or it's the slowest step in a process. So from the traditional name of the that it comes from, the bottleneck becoming the limiting resource, or in a operation, the slowest step, which in our case is the packing step, 60 seconds. So when we look at this operation, this fulfillment center has an approximate maximum capacity of about 480 units a day. And I say approximate because it is possible to probably generate a few more of these units if you were looking at it filling up the time precisely. But it gives you a very good ballpark of what that operation is capable of doing. Now, we have to define this word WIP to really understand the full story. It's called work in process. And when we think of WIP, the technical definition says a good or goods in various stages of completion throughout a plant or an office. Traditionally, all materials from raw material that has been released for processing up to completely processed material awaiting final inspection, aka finished goods, is what we know WIP to be. And in our supply chain world, this is very, very familiar to us. But in the service industry, we also have WIP. Think of WIP as those unfinished customer requests. They're in process. The emails that you have to respond to because you're on this webinar with us for the next 45 minutes. The phone calls that are waiting in your queue because you're on this webinar. Those reports that you've got to complete to your manager or to your team. Those are also what we call WIP. Now, WIP and bottlenecks have a very interesting relationship, and I'm going to depict this relationship with a simulation. The simulation is based on that sample fulfillment center that we just walked through. So let's take a look at this. We know the picking station takes 30 seconds to do that work. The inspection is another 10 seconds. Packing is 60 seconds. And we know that's the bottleneck, the slowest step in our process. Then there's the labeling, 10 seconds, and finally the seal operation, just 5 seconds. Now, in business, this is what happens typically. Those folks at the picking station are going to continue picking those items. They're not going to stop and wait till the seal operation is complete. So they're building up at least 3 units of excess WIP before they're even actually needed. Now, the same goes for the inspection. The inspector is building up a glut of perhaps 7 units of WIP before they're really needed. And our packing station is also generating a little bit of WIP here before it's typically needed or truly needed. Now, look at what happens on the other end of the bottleneck. The labeling and the sealing operations are what we call starved for resources because they're waiting to get those items from that bottleneck. And so what you have is this two-tiered type of two-pronged issue. On one hand, in the early stages of the operation, we've got too much WIP, too many lost pieces, documents getting lost or damaged, confusion, delays, we're taking up storage. And the flip side, at the other end of the WIP or the bottleneck, there's just not enough. And our operators are idle, shipping delays. And so this is why we need to balance this line, because we're creating these two very, very problematic issues. And I should preface the scenarios that we're working with here, the fulfillment center, 1 worker per station is the assumption. Now, capacity utilization is another way to analyze our operation. It essentially is a measure, and it's expressed as a percent of how much capacity of an operation is being used. It just provides another window into how our operation is being utilized. And the definition to calculate it is to take the capacity at the bottleneck, and that's going to be in terms of number of units, and we divide that by the capacity available at a particular step in terms of the number of units at that step. Now, capacity utilization, it provides a window into how efficient each step is relative to the capacity of the bottleneck. So let's try back to our fulfillment center. Again, demand at this center is 10,000 orders a month or 500 orders per day. Hours of operation, 8 a.m. to 5 p.m. with a half hour for lunch and 2 15-minute breaks. And our question is, what is the capacity utilization at each step? So here's that value stream. So for step one, the picking operation, we're going to take the bottleneck capacity, which we know from the previous exercise was 480 units a day, and we're going to divide it by the 960 units that that particular step had the capacity for. And we come up with a 50% capacity utilization for the picking station. And here are the rest of those steps in terms of how well they're being utilized. So you see steps 1 and 2, 4 and 5 have a utilization of very small, very low. In other words, they've got ample buffer. But station 3, the packing, is at 100% utilization. It's running flat out. So let's interpret what this utilization metric really does show us. Look for those steps with low capacity utilization, as this indicates what I said, excess buffer. Operators may be idle, which presents an opportunity to increase their utilization. Now, conversely, or in reality, workers are rarely idle. Normally, they continue working and multitasking. And if you notice workers building up more WIP, this should be a red flag to you, because when WIP starts building up in your operation, you're immediately behind the 8 ball. It takes up space, WIP can get lost, damaged, and you can never get your arms around it. Once it starts building up, it has no conscience. Conversely, pay attention to steps in your business with very high utilization rates, because this indicates there's very little buffer. Notice step 3 is 100% utilized. Those workers can be overworked, and that leads to fatigue, accidents, defects. So we've got to look at the utilization in terms of its impact on our business. So now that we've defined step 2, calculating your capacity, Michael is going to share the example at Proterra, his company.
Thank you, Peter. So we at Proterra faced a similar issue as what has been described in this example. But first, a little bit of background about us. Proterra Incorporated is an American automotive and energy storage company. We design and manufacture electric transit vehicles, as well as the electrical charging systems that go with them. So, as I said, we have a similar scenario to what was discussed in the earlier example. Our current production line was capable of producing 1 vehicle every 2.5 weeks. However, our demand was far greater than that, roughly 50 vehicles per year. So our goal, tasked to us by our management, was to update and improve the line in order to produce 1 vehicle every week so as to keep up with our customer demand. So looking back and revisiting step 1, which is determine customer demand, we've done that. That's 1 vehicle per week, or roughly 50 buses per year. So the next step is to determine the takt time. Our hours of operation are 6 a.m. to 3 p.m. with a half-hour lunch and 2 15-minute breaks, and that's 5 days a week. Again, the demand is approximately 50 buses per year. So removing the time used for lunch and breaks. That leaves us with 8 hours of production per day, and that's 5 days a week, so that's 40 hours per week. And again, the demand is 1 vehicle per week, so taking the available production hours and dividing it by demand gets us 40 hours per vehicle, or 1 week. Our current production process, or our production process at this time, was a 7-step process as indicated by that flow just below that calculation there. So now that we know our takt time, our next step was to evaluate the capacity and determine the bottlenecks in our 7-step process. So our objective, what is the capacity of each station? And if you'll remember to the earlier slide discussing capacity, the equation is the available production time divided by process time per unit. So we're going to start with station 0, which station 0 is the first step in our process. Available production time, again, 40 hours per week. And the process time for this station, as indicated by that table there, was 99 labor hours per week. So our capacity equated out to 0.4 vehicles per week, which means in a week's time, we were able to complete 40% of the vehicle, which lines up with our 2.5-week lead time for our vehicles. We then did this calculation, the capacity calculation, and carried it through to the remaining 6 stations. You can see in the bottom flow that those capacities are laid out just below the title. And you'll notice that we didn't have 1 bottleneck. We, as a matter of fact, had 6. So the first 6 steps in our process were actually over that target takt time of 1 vehicle every 40 hours. So now that we have our capacity and we're able to identify our bottlenecks, the next step was to determine the capacity utilization for each station. Capacity utilization, if you'll remember, was the capacity at the bottleneck divided by the capacity available at each step in the process. So again, starting with station 0, our capacity was 0.4 vehicles per week. And the capacity at that step was also 0.4 vehicles per week, which when crunching the numbers, you'll find that at station 0, we are already at 100% of our station's capacity utilization. So the takeaway from this is station 0 was maxed out. And then once we ran the numbers for the remaining stations, stations 1 through 6 are significantly underutilized. Hence, the line is not balanced. So now that we've done the Proterra a lead into the Proterra example, Peter's going to walk you through the 3rd and final step in the process, and that's balancing the line.
Thanks, Michael. Okay, so step 3, we're ready to start balancing the line. And the key tool to do this is what we call an operator loading chart. It's a very graphical tool that combines the process times of each step with the takt time. And the beauty of a operator loading chart is it's highly visible. It's simple to explain. So back to our fulfillment center, we take all of the process steps and put those on the horizontal axis: picking, inspection, pack, label, and seal. And on the y-axis, we put in the process time for each step. The next thing we do is to overlay the takt time. And if we remember, the takt time in this example was a little less than a minute. So every point where you see any of the bars exceeding that takt time tells you that there's a bottleneck. Conversely, any of those process steps that are lower than the takt time indicate there's ample buffer. So this is what we call an operator loading chart, and it's a very key tool to help us in our journey. Now, Michael is going to share with you the Proterra operating loading chart at his operation, what used to be.
Thank you, Peter. So using the tool that Peter just explained to us, I was able to take, or we, I should say, were able to take, there's no I in team, we're able to look at the station or the assembly process in a graphical manner. Now you'll see that our takt time is that red line splitting the screen, and that's at 40 hours. And this representation shows us that station 0 is, well, far exceeds our takt time. That being said, as do stations 1 through 5. This was a very valuable tool in the Proterra example because we were able to take this to any level of associate, whether it be assembly or management, and really kind of explain how and why our process was where it was. So breaking this particular chart down, we were able to determine that our current layout does not allow us to meet the new customer demand. And stations 0 through 5 are greater than the takt time, thus they are all bottlenecks. And station 0 was by far the largest offender. What it really helped us to find out was that this 7-station layout was very congested. There were too many operators in each station. They were bumping into one another, getting in each other's way, causing holdups, waiting for one another to complete tasks. And coincidentally, it also resulted in a number of quality defects, scratched parts being left on the floor while people were waiting. It wasn't a good setup. It wasn't conducive in allowing us to reach our target takt time. The curveball for us was many of the steps in our process require serial completion. And what this meant is we weren't just able to simply reallocate tasks from one station to another. It was a little bit more complex than that. Thankfully, there's a number of different methods that you can employ when you're looking to balance out your line. Peter will take you through those right now.
Thanks, Michael. Okay, so what we're going to share next are 13 different ways to balance the line, 12 of which do not require capital or extra headcount. And that's what makes this, I think, very, very intriguing for participants on this webinar. So let's run through these 13 different options. Option 1, we could distribute work to underutilized workers. So let's take a look back at our fulfillment center. Here's that operator loading chart. And what it says here is that the pick, inspect, and seal operations have a lot of buffer. We might consider sharing half of the pack work with the inspection worker. This would mean adding maybe a half a minute of process time to the inspect worker while reducing a half a minute of time from the pack worker. And in figure B, we show the new balanced operator loading chart. We've removed the bottleneck at the pack station, and very interestingly, we have increased capacity now from the 480 units to 720 units per day. Caveat, distributing work is not always possible where there might be physical constraints or tools that are in limitation, or the scenario that Michael was describing where it required serial completion, but it also requires some cross-training, but it's a very, very good option to consider. Now, option 2 is about consolidating work functions. Operator loading chart B up here, now that we've made the balance, shows that the label and the seal steps are sequential. They're inherently similar in scope, and they've got sufficient buffer to consider consolidating. And we could combine these two steps. And that would have the very interesting benefit of freeing up one worker for other activities. And here's our new operator loading chart. Again, consolidating work functions could require some cross-training, but a much better option than having to add headcount or equipment. The third option in our repertoire is to utilize what we call pull systems. Pull systems control flows of resources in a production process by replacing only what has been consumed. And when we talk about this, we say production is driven based on actual demand and consumption rather than forecasting. The central part of a pull system is what we call the Kanban card system. And Kanban is a Japanese word. It literally means the signal. And it's a signal for an operator somewhere along the line to trigger them to do something. It triggers the flow of materials, production of operations. And the ground rules of a Kanban symbol are very simple. Each workstation in that production line is going to produce only when they receive the Kanban card or the signal from the previous workstation. And when you have this Kanban, you get this incredibly powerful balancing, load balancing with your inventory. A related type of option to the pull system, one that goes very well, is what we call reducing the batch size. Now, in our example, we've assumed orders in this fulfillment center are being processed or batched one at a time at each step. And this is what we call one-piece flow. Now, the benefits of one-piece flow are very, very significant. It reduces overall lead time. We can get product out to our customers much faster. It keeps WIP at a minimum, and it has this added benefit of increasing our flexibility to respond to those changes in customer preferences if they happen. On the flip side, one-piece flow also could add costs associated with more frequent setups for those changeovers. So one-piece flow is a very sound way to balance the line, to create flow. But the question, I guess, is everyone's mind is, well, why wouldn't a business want to produce large batches? I thought large batches is always more efficient. And there is a benefit to large batch sizes. Generally, it's those economies of scale achieved through bulk discounts from those suppliers and fewer changeovers required. Batching, though, has its limitations. Process time increases, which reduces capacity and creates that buildup of WIP. Just to continue this, imagine if our fulfillment center fulfilled orders in batches of 5. In other words, work could only be released to the next step after 5 orders were completed from the previous step. The table at the right here shows the impact of this type of configuration. And look at what happens to the packing station. It becomes the bottleneck at only 96 units per day. Remember, at one-piece flow, we were producing at least 480 units. If we were to batch this in items of 5, we would actually reduce our capacity. All right, option 5, reduce those defects. Always very sound guidelines. When you reduce defects, you reduce the time associated with rework. It just makes sense. This helps to balance the line and create that flow that you need. Option 6 involves getting organized. Organize it in your work area. So, for example, moving those workstations closer together, eliminating that walk time, sequencing your material flow from right to left. And this is an interesting ergonomic approach. Most people are right-handed and right-eye dominant, and flowing that material operations from right to left is generally faster. Try setting up those workstations before the operation starts opening up for business. You want to let the front line hit the ground running, minimize their downtime. Obviously, we want to eliminate any non-value add activities, such as excess motion, by putting those supplies and tools closer to where they're really needed, at the workstation. And finally, we could look to optimize the changeover process. Can we strip out any unneeded downtime? And if anyone has ever seen the pit crews in a Le Mans car racing or a Grand Prix or even stock car racing, you see the changeover of those automobiles is incredibly well orchestrated. It only takes maybe 5-6 seconds at the most to change over and replace the tires, refuel the engine, clean the windshield. Continuing on with our options to balance the line, option 7 is reduce the deep downtime due to any equipment failures. Preventive maintenance is always a sound policy. Let's prevent equipment from going down. In a similar vein, if we have to do maintenance or upgrades on our equipment or IT, let's do it during off hours. Let's not impact the available work time. Option 8 is about paying attention to your inventory. Inventory can be a very, very good asset in terms of balancing the line. And when I say that, I'm talking about maintaining adequate inventory levels to prevent those work stoppages. Conducting inventory cycle counts off hours. Don't impact that available working time. Option 9 is improving the scheduling of your operation. So the internal scheduling. Here's a very interesting one. Consider increasing the uninterrupted work time by your team by scheduling those lunch breaks at the end of the shift. I've seen a lot of examples of organizations that have done this, and it has a very interesting benefit of minimizing delays that are associated with getting folks back to the job from their lunch breaks. Staggering those breaks and lunches for work crews also creates more of a continuous flow. No need to have everybody on the line take the same break at the same time, but try staggering it. Create the flow. Now, this next option, 10, is regarding safety. If you could create a safe work environment, you're going to help yourself, because any downtime from work-related injuries is going to get prevented. Option 11 is getting with your customers and try level loading the demand. So Michael talked about this. Work with your customers to improve the demand forecasting. Good forecasting can smooth out that demand. Option 12 is to utilize overtime. And as a variable cost, overtime can be very cost effective. In an interim approach, the danger is when overtime becomes the norm, and it can get very expensive, and it also poses a safety risk. Finally, our last option, 13, if all else fails, we could consider adding headcount and or machinery, but we should always use this as a last option because of that investment cost and fixed overhead. It could be financially justified, but I do want to stress it is probably the last thing to consider. So here we've got 13 options, 12 of which do not require added headcount or fixed equipment. So with that, Michael is going to walk us through how he and his team approach balancing the line at Proterra.
Thank you, Peter. So coincidentally, step 1 for us at Proterra was option 1, and that was distributing the workload to underutilized stations. So we kind of took our own spin on it, and we broke up the 7 stations into 13 stations. Now, you remember our original flow. What we did is we took that station 0, that worst offender of the bottleneck, and we broke it out into 3 stations. We were having a number of quality defects, and so we broke, I'm out of order. In addition to breaking up station 0 into 3, We also took our rooftop assembly, which took a lot of time, and broke it up into 2 stations, as well as our interior fit and finish. What this allowed us to do was implement 2 inline quality inspection stations, which helped to significantly decrease the amount of quality defects we got at the end of the line. So our new flow, as you can see, begins with the 3 body prep stations. Right after that, we have our first quality inspection. After that, we jump into the underbody assembly, interior electrical, and then you have rooftop 1 and 2. And then directly following that, we have quality 2. Following that, we have interior fit and finish 1 and 2, and then battery install. And the final step in the process is vehicle commissioning, which in essence is turning it on and letting it run. So again, these changes reduce the process time per workstation while also reducing the operator congestion and improving quality. The next slide will show you our station loading chart. So you can see that we still have our 40-hour takt time, but now each one of these 13 stations is below that target takt time. So the quality inspection stations that happen in process at the end of the line again allowed us to really kind of streamline things and reduce rework time that was involved with the process, while also increasing station safety by reducing congestion. Station 5 did require 8 additional man hours. This was offset by increased productivity and resulting revenue. To further increase or improve our takt time, we have considered overtime for our operation. The next step in our process was to look at options 5 and 6, which, if you'll remember, option 5 was to reduce or eliminate defects, and option 6 was to organize your workstations. So organizing workstations, we by breaking up the stations into smaller, more numerous stations, we're able to design smaller kit carts, which took up less space and were easier to organize and move. In addition to that, we had whip carts developed, which allowed us to store work in progress and keep it from getting damaged. Finally, we designed and implemented tool boards, which allowed each station to be better organized, and the work areas were a lot cleaner, safer, and they also we minimized wasted space and time wasted searching for tools. So really, by addressing organizing the workstations, or option 6, it really kind of cascaded and allowed us to address option 5, the defects, and really just kind of improve our overall station and product quality. So with that, I'm going to turn it over to Peter to summarize what we've talked about.
Thanks, Michael. And I bet you those improvements were very low cost too. The kit carts, those boards, and so forth, huh?
Yeah, they didn't cost us a whole lot, but they paid dividends in what we were able to accomplish, and just the overall look of the place too. It was a whole lot cleaner, a whole lot better place to work. Absolutely.
Thank you. All right. So in summary, we have covered a lot of ground here, and creating flow in any operation, whether it's a fulfillment center, a manufacturing line, or even a service operation, is key to meeting your customer's demand and at the same time optimizing your resources. We encourage you to share this 3-step approach with your front line, explain these concepts like takt time and bottlenecks, and demonstrate how to use and interpret these tools, many of which are very easy to learn and to see, like that operator loading chart. And in doing this, you'll be able to create what we call a win-win-win. Your customers are going to be satisfied, the front line is totally engaged in the process, and the business is profitable. So with that, we want to thank everyone for taking time in this webinar. We've covered the challenge, we've defined lean and flow, and then we've walked you through this 3-step approach to streamlining your operations. Before we continue with the Q&A, did want to take one brief timeout. We've got several Lean Six Sigma certification workshops we're conducting here in the Southeast. Atlanta, Charlotte, Chattanooga, Greenville. These are very practical skill sets where we're going to learn how to utilize these tools we've covered in more detail. And webinar attendees receive a $100 discount on the yellow belt, which is the introductory workshop, and $500 on the green belt workshops. And the number to call is there and my email address. With that, Kia, I will turn it over to you with any questions you've got from the audience.
Thank you, Peter. We just have a few minutes, so please, everyone, as a reminder, look to the right toolbar on your screen and type your questions in the questions box and click send. A few people have been asking questions already. So the first one I have, there were a lot of questions about determining if your business is a push flow or a pull flow. So this person asked, in a business with a long lead times, more aligned to push flow, and at the same time complex and more aligned to pull flow, how can the most suitable flow be defined?
You know, that's a terrific question. I think it depends on the nature of the business. What the principles we've laid out are just that. They're guidelines based on experience from many different industries. I think you've got to look at the context, look at the sensitivity to the customer. For example, we're in the cold and flu season right now, and if the drug manufacturers were to wait until a flu outbreak occurred to start producing flu vaccinations, that would be very, very dangerous from a health perspective, safety. And so drug companies will push production out because they know they can't wait until the first outbreak. So I think the context is definitely critical. Michael, do you have any input on that?
No, honestly, I think you hit the nail on the head with that. It is very dependent on what your customer wants. I mean, there's no one right or wrong answer. It's not black and white. For us, I mean, we have long lead times with our product, but at the same time, we are still a pull system. It just really depends on all the individual attributes that your business consists of.
Great. The next question I have is, did you consider OEE rates when you evaluated your takt time, or was your takt time evaluated assuming 100% OOE rate?
Another very good question, that operational effectiveness, overall equipment effectiveness. Takt time has to incorporate that available operating time divided by the demand. And when you talk about available operating time, we naturally have to think about the operational equipment effectiveness or overall equipment effectiveness. For example, downtime or equipment uptime, that's a key component of OEE. So the answer to your question is yes.
Excellent. And so for the last question, can you recommend a sound approach for implementing Lean to a company or a department?
That is a very good question. How would you approach this? And I think the best approach that I can think of is to have a candid conversation with your team to help them understand the problem. And I like to start with the why. In other words, the context of why is this so important? Why do we need to change the flow of our operations? Is it because customers are demanding shorter lead times? Or maybe expediting costs are totally eating into our profits? Perhaps maybe our internal ops just cannot keep firefighting. Once you get people to understand and agree on that fundamental question, then you've generated buy-in. And implementing the process is going to be much easier. I would recommend, and I think Michael could share with this, start with a small part of your operation. Don't try to tackle all 7 stations at one time, and use the 3-step approach that we've just outlined.
Yeah, absolutely. I know that for Proterra's example, we started with Station 0, our worst offender bottleneck, and that's actually where we really kind of stuck there until we felt that we were ready to move on to Station 1. And when I say we really stuck there, I mean we broke it up into the 3 stations and then really tried to figure out how to best improve our quality as well as our station organization. And a lot of what we learned in that station, we were able to carry through and implement to the remaining portions of our process.
All right, I think that's all the time we have for today. If anyone didn't have their question answered, feel free to contact Peter or Michael with their contact information. If you could pull up that slide, and you can ask them directly. We'd like to thank our speaker and all of our participants for their time today. This concludes today's edition of APICS Extra Live. Please mark your calendars for the next APICS Extra Live presentation on March 8th. You can learn more and register for this event in the near future at apics.org/online events. All content and materials included in this edition of APICS Extra Live are the property of APICS and are protected by the United States and international copyright laws. All rights are reserved.